Welcome to Surveying and Geospatial Insights, the podcast dedicated to the science of precision. I'm your host, Survey Steve. At the absolute heart of our profession lies a single fundamental goal: to make measurements that are both precise and accurate. But no measurement is ever perfect. Every observation we make contains some degree of error. So, today, we are going to explore a topic that is the very foundation of professional practice: minimizing measurement errors. We'll discuss the different types of errors, where they come from, and the rigorous procedures we use to eliminate or reduce them. Joining me today is my colleague and measurement theory expert, Debora. Welcome.
Thank you, Steve. It's a pleasure to be here. This topic is everything. It's what separates a professional surveyor from a technician. Anyone can be trained to operate an instrument, but a surveyor's true value lies in their deep understanding of error theory and their disciplined application of procedures designed to produce reliable, defensible results. Understanding error isn't about admitting failure, it's the first and most critical step toward achieving quality.
An excellent point. To start, it's essential to understand that not all errors are created equal. In surveying, we classify them into three distinct categories: blunders, systematic errors, and random errors. Let's begin with the most straightforward and, frankly, the most embarrassing: blunders, which are also known as gross errors.
Even taking notes in a field book requires a disciplined process. A professional surveyor will use a standardized format, clear sketches, and will never erase a suspected mistake. Instead, they will draw a single line through it and write the correct value nearby, preserving the original entry. This maintains the integrity of the record and allows someone in the office to understand the thought process and catch a potential misinterpretation. It's a simple but powerful procedure for preventing blunders. Even taking notes in a field book requires a disciplined process. A professional surveyor will use a standardized format, clear sketches, and will never erase a suspected mistake. Instead, they will draw a single line through it and write the correct value nearby, preserving the original entry. This maintains the integrity of the record and allows someone in the office to understand the thought process and catch a potential misinterpretation. It's a simple but powerful procedure for preventing blunders. Blunders are simply mistakes. They are the result of carelessness, inattention, or a misunderstanding of procedures. Examples are everywhere: transposing numbers when writing them down, like recording 52.13 instead of 52.31. Measuring the height of an instrument to the wrong mark on the tripod, citing the wrong survey target, or even forgetting to level the instrument properly before you begin. These errors are typically large, unpredictable, and they are not governed by any mathematical law. Blunders are simply mistakes. They are the result of carelessness, inattention, or a misunderstanding of procedures. Examples are everywhere: transposing numbers when writing them down, like recording 52.13 instead of 52.31, measuring the height of an instrument to the wrong mark on the tripod, citing the wrong survey target, or even forgetting to level the instrument properly before you begin. These errors are typically large, unpredictable, and they are not governed by any mathematical law.
And they're insidious because a single blunder can contaminate an entire project. It's not just about wasting a day's work. It could lead to a fence being built in the wrong location, a bridge abutment being poured incorrectly, or a major boundary dispute between neighbors. The financial and legal consequences of an undetected blunder can be enormous, which is why our entire profession is built on a foundation of procedures designed to catch these very mistakes. That's a critical point, and it highlights the importance of independent checks. One of the best ways to catch a blunder is to have a completely separate and redundant measurement. For example, after running a long traverse, you can use a GNSS receiver to independently measure the coordinates of the start and end points. If the GNSS-derived distance between those points doesn't match the distance derived from your traverse measurements, it immediately signals that a problem, likely a blunder, exists in your work. It's about creating a check that is external to the primary measurement process itself. The key takeaway for blunders is that they must be detected and eliminated. They cannot be treated mathematically. A single undetected blunder can invalidate an entire day's work. This is why strict field procedures and redundancy are so critical, but we'll get more into that later.
The next category is systematic errors. Unlike blunders, these errors are predictable. They follow a specific mathematical or physical law. If you repeat a measurement under the same conditions, a systematic error will have the same magnitude and the same sign, either positive or negative. For example, a steel tape that is physically 1 millimeter too short will make every single measurement you take with it 1 millimeter short per tape length. This is a predictable, cumulative error.
Other great examples include an instrument's leveling axis not being perfectly perpendicular to its vertical axis, or the effect of temperature and atmospheric pressure on an electronic distance measurement, or EDM. Because these errors follow physical laws, we can often model them. We can then either use procedures that cancel them out, or we can apply a mathematical correction to remove their effect from our raw measurements.
Finally, we have random errors. These are the small, unavoidable discrepancies that remain after all blunders have been eliminated and all systematic errors have been corrected. They are caused by factors beyond the control of the observer. Things like the limits of human eyesight when pointing an instrument, slight variations in atmospheric conditions, or microscopic imperfections in the instrument's construction. These errors are governed by the laws of probability. They are just as likely to be positive as they are to be negative, and over many observations, they tend to cancel each other out.
So to recap, blunders are mistakes we must eliminate. Systematic errors are predictable biases we must correct for. And random errors are the residual statistical noise that we must manage.
Now, let's discuss how we apply this theory in practice, starting with our procedures in the field. The first line of defense, against blunders in particular, is redundancy. A professional surveyor never relies on a single, unchecked measurement for anything important.
Exactly. This principle is built into all of our standard procedures. When we run a traverse, we close the loop, either back on our starting point or on another point of known position. The misclosure of that loop is our check. If it's a large, unacceptable value, it almost certainly indicates a blunder somewhere in the network that must be found and remeasured. When running a level circuit, we do the same, closing back on a starting benchmark to check our work.
For systematic errors, our field procedures are designed to either determine the necessary correction or to cancel the error out entirely. A prime example is how we turn angles with a total station. We first point to our back sight, then our foresight, and record the angle. That's a face 1 or direct measurement. Then we plunge the scope and rotate the instrument to repeat the measurement. This is a face 2 or reverse measurement. By averaging the direct and reverse angles, we mechanically cancel out several significant instrumental errors, like the collimation error, without ever having to calculate them.
And of course, we must apply corrections for those systematic errors we can't cancel out. For EDM measurements, this means diligently measuring the air temperature and pressure and inputting them into the instrument so it can calculate the atmospheric correction. It means ensuring we are using the correct prism constant for the specific target we are using. These aren't optional steps, they are fundamental to achieving accurate results. This all goes back to proper instrument calibration. A surveyor must regularly check and adjust their equipment, performing peg tests on levels and collimation checks on total stations to ensure they are in good working order.
Finally, to manage random errors, we rely on repetition. The theory of probability tells us that the mean of a series of repeated measurements is more likely to be the true value than any single measurement. So for high-precision work, we don't just turn an angle once direct and once reverse. We might turn a set of 4 or 6 repetitions. This repetition helps to minimize the effect of the small random errors in pointing and reading, giving us a more reliable final average.
This rigorous approach continues when we move from the field to the office. The first step in data processing should always be a careful review of the raw field data, whether it's from a digital data collector or a handwritten field book. You're looking for anything that seems out of place, for notes from the field crew that might explain an oddity, and for potential blunders that weren't caught on site.
Once the data is vetted, the most powerful tool we have for dealing with error is a least squares adjustment. This is a statistical method that is ideally suited for survey data because our work is filled with redundant measurements. A least squares routine takes all of our measurements, angles, distances, elevations, and adjusts them all simultaneously to find the most probable set of coordinates for our survey points.
The magic of a least squares adjustment is twofold. First, it ensures the final geometry is perfect. A traverse loop that had a small random misclosure in the field will be adjusted to close perfectly. Second, and more importantly, it provides a rigorous statistical analysis of our work. It can help us identify remaining blunders by flagging measurements that have large residuals. It also computes the final estimated precision of every point in the survey, often represented by an error ellipse. This allows us to state, with a specific level of statistical confidence, how accurate our final positions are.
This final statistical report is incredibly important. It's no longer enough to simply say a survey is accurate. We must be able to prove it. A proper least squares adjustment provides that proof. It's the ultimate culmination of our efforts to manage error, from our first setup in the field to the final calculation in the office.
So, in summary, the management of measurement error is a systematic process. It begins with adopting rigorous, redundant field procedures to identify and eliminate blunders. It continues with the careful calibration of equipment and the application of corrections to remove systematic errors. And it concludes with the use of repetition and sophisticated statistical analysis, like least squares, to manage random errors and produce a final defensible result with a known quality.
It truly is the defining characteristic of our profession. We are the experts society relies on to understand, quantify, and minimize error in spatial measurement. This discipline and this knowledge are the true sources of our value.
Well said, Debora. Thank you for breaking down this complex but essential topic for us. And thanks to our listeners for joining us on Surveying and Geospatial Insights.